Alright, so in this video I'm gonna be explaining another important article about domain adaptation. The title of this article is Adaptive Risk Minimization, Learning to Adapt to Domain Shift. So this paper from Stanford University. A fundamental assumption for most machine learning algorithms is that the training and test data are drawn from the same underlying distribution. We call it IID, Identically Independent Distribution, IID. However, this assumption is violated in almost all practical applications. Machine learning systems are regularly tested under distribution shift due to changing temporal correlations, atypical end users, or other factors. In this work, we consider the problem setting of domain generalization, where the training data are structured into domains and there may be multiple test time shifts corresponding to new domains or domain distributions. Most prior methods aim to learn a single robust model or invariant feature space that performs well on all domains. In contrast, we aim to learn models that adapt the test time to domain shift using unlabeled test points. Our primary contribution is to introduce the framework of adaptive risk minimization, in which models are directly optimized for effective adaptation to shift by learning to adapt on the training domains. The standard assumption in empirical risk minimization is that the data at test will match the training. When this assumption does not hold and there is a distribution shift, the performance can deteriorate significantly. So this is an example. We consider handwriting classification. After training on data from past users is deployed to new end users. Each new user represents a new test distribution that differs from training distribution. And there are many examples. So in this paper, we instead focus on methods that aim to adapt a test time to domain shift. We study problems in which it is both feasible and helpful to assume access to a batch or a stream of inputs at test time. And their main contribution is to introduce this framework of adaptive risk minimization, which proposes the following objective. Optimize the model such that it can maximally leverage the unlabeled adaptation phase to handle domain shift. So, our formal goal is to optimize for expected performance, for example, classification accuracy at test time. To do so, let us first consider predictive models of the form F, where the model F takes in not just an input X, but also the marginal input distribution that X was sampled from. We refer to F as an adaptive model, as it has the opportunity to use P sub X to adapt its predictions on X. The underlying assumption is that P sub X provides information about Py condition on X. So when P sub X provides information about P of Y condition on X, and then training and test domains are drawn from the same distribution over P, we can establish favorable generalization bounds for the expected performance of F in adapting to domain shifted test time. We can formalize this like we define first a prediction model to be a non-adaptive model, and define the risk for a prediction model G and loss function under a data distribution. So we define a base optimal risk like this minimization. So mu denote the distribution from which training and test domains are sampled. To avoid overlapping terms, we define the adaptive risk for an adaptive model F and L. So expectation over mu, that distribution on P of x and y, also expectation on P of xy. So let F star denote a minimizer. If mu is a distribution on P such that mu almost surely it holds that P of y condition on x is equal to M for some deterministic mapping M, then we have this relation. So in other words, an adaptive model which minimizes adaptive risk coincides with a Bayes optimal decision function. We wish to learn an adaptive model to tackle domain shift. So meta-learning methods for label adaptation study a similar form of a model. And a common approach in many of these methods is to define F such that it is composed of two parts. First, a linear which ingests the data and produces parameters, and second, a prediction model which uses these parameters to make predictions. So we will decompose the model F into two modules: a standard prediction model that is parameterized by theta and predicts y given x, and adaptation model which is parameterized by phi. H takes in the prediction model parameters theta and k on labeled data points and uses the k points to produce adapted parameters. The ARM objective is to optimize phi and theta such that H can adapt G using unlabeled data samples. Note that this E is the empirical form of adaptive risk for the form of F we have defined. Mimicking the generative process, we assume generated the training data P sub Z is a categorical distribution and which places uniform probability mass on its training domain. So we require training step batch size k and learning rate gamma, and then we sample Z uniformly from training domains. Then we sample x and y from this distribution, and then we just update it. But at test time, we record theta and phi, and then we update. We also instantiate the model with a prediction network parameterized by theta when given a mini batch of input. If count processes each example in the mini batch separately and outputs this ck. D is a type of parameters, and in our experiments we choose D to be dimensionality of X such that we can concatenate each image and the context C along the channel dimension to produce the input to F. So F of prediction processes each X separately to produce an estimate of the output, but it additionally receives C as input. In this way, fcont can provide information about the entire batch of K unlabeled data points to F of prediction for predicting the correct outputs.